interesting as I do. So we start here. We want to talk about a reasoning behind the fundamental theorem of calculus. Who knows the fundamental theorem of algebra? Y equals mx plus b is totally incorrect.
I thought it was so right.
Fundamental theorem of algebra. Fundamental theorem of algebra says that if a polynomial has degree n, it has exactly n solutions. And it can be written in factored form. Every single polynomial can be written in factored form. This one factors to 3 parts. And if there's an imaginary solution, they always come in pairs. If there's going to be one, there's going to be another one. That's what the fundamental theorem of algebra says. But you guys remember that if it's a degree 3, there's going to be 3 solutions, right? Okay, so fundamental theorem of calculus. What is it? Today you learn it. Let's start with this idea. We are going to look at an area from A to X, and then a little slice on over to X plus H. What is the distance between X and X plus H? Very good. I would like to write an expression for the small area. Can everybody see here that I have 3 different areas? I have this this small area. I then kind of have this medium-sized area. If you put the 2 together, you get the big area. You see that? So, give me an expression. Small area is equal to. Don't use X plus H. Use words like big and small and medium. Big area minus medium area. Can you see that up there? Okay, so this small area is the same thing as the entire area minus the medium area. See it now? If I were to color it in blue and red, we would say that the red is equal to the whole thing minus the blue. We good? Okay, then let's write some calculus expressions to show that. Namely, the small area we are going to say is equal to the integral from x to x plus h of f of t dt. That integral symbol is the calculus symbol that we're going to learn what to do today with, but it means the area bounded from x to x plus h. Sorry, f of t dt. And that's going to be equal to the big area, so I bound it from what to what? A to x plus h of f of t dt. And I subtract, the medium area would be integral from a to x of f of t dt. How are your integral symbols going? Okay. Are we all okay with that expression? Then what I would like to do is I would like to focus on this small area. And I would like to suggest to you that this small area right there, I'm going to approximate it. And I'm going to approximate it by drawing a rectangle. Would you agree that that's approximately the same as the shape that we were looking at? I mean, it's close. Okay, how would we find the area of that rectangle? We take the base times the height, right? What's the base? What's the length of the base? H. And then how would we find the height? Yeah, not f of h necessarily, but we plug in what value? Where are we evaluating the height? You tell me where. Aren't we evaluating the height right here? And we plug in x, what do you get? F of x, right? Okay, so suppose that this function is y equals f of t, which is what it is, and suppose that that x value was 4. How would you come up with the height? Yeah, so I'm going to plug in x, and I get f of x. So that's the height. So h times f of x. And instead of doing an equal sign, we're going to do approximate sign. Over the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. H times f of x, a to x plus h, f of t dt. So all we did in that situation is we just took this area right here and we wrote it as the area of a rectangle that we approximated. The width was h and the height was f of x. And they're about the same. I'm going to do one other thing, and I'm going to divide both sides by h. So f of x is approximately the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt, all divided by h. What do you think? Does it look kind of nasty? Okay, so you're almost ready to kind of make the aha moment. The last thing I'm going to do is suggest this. Would you agree that this area, this rectangle, is going to become a better approximation the smaller it gets? So the smaller this rectangle gets, it's going to better approximate that exact area. So if I want to make this rectangle smaller, what could I do? What could I do to h? Yeah, bring h closer to 0. The way that we bring things closer to something is we use a limit. So I can write this as f of x is equal to the limit as h goes to 0 of the integral from a to x plus h f of t dt minus the integral from a to x of f of t dt all over h. I'm going to give you 45 seconds. You should see something that is from your past time in calculus that hopefully rings a bell. I don't think everybody will see it, but maybe, I don't know, 8 of you will see it. Talk with your partners, those around you, see if you see something, anything that you're like, I think I've seen that before. Go. Okay, who's anybody sees something they're like, I think I remember that. There was a thing over H at the beginning of the year, so says Colin. Anybody else kind of, you're like, yeah, I think I remember seeing something over an H at the beginning of the year. Does it look like this? F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Do you remember that? Now, so I need to help you make the connection because right now just recognize that it doesn't really make the connection. But what we can see is this. First of all, that's how we first found derivatives. You remember that? And so we had like we had like this thing. We had, say, suppose that the function, suppose f of x was x squared. Then you would say we would do the limit as h goes to 0 of x plus h quantity squared minus x squared all over h, right? And we worked on like simplifying that, didn't we? Like let's actually do that. What's x plus h squared? X squared plus 2xh plus h squared minus x squared all over h. You said everything that doesn't have an h should cancel. And does that happen? Yep. And then we should be able to divide an h off. And if you divide an h off, you get the limit as h goes to 0 of 2x plus h. Can we now let h go to 0? And when we do, what do we get? 2x. Are you surprised that we come up with the derivative of that thing is 2x? Are you glad we don't have to do that all the time anymore? Yeah, I mean isn't that, we did one of the easy ones. You're like, oh my gosh, is it taking me forever, right? Like, you know that this answer is x squared, right? I'm sorry. You know that this answer is 2x. Like, you can look at this expression right here and you can see, oh, that's the function and it's going to give me the derivative, right? Okay, so help me out here then. Suppose I were to write this. The limit as h goes to 0 of x plus h quantity cubed minus x cubed divided by h. What's the function? X cubed. Everybody agree? So what's going to be the derivative? Yeah, you already know just by looking at this that you're going to get 3x squared, right? You already know. Because you see, that's the function that you're going to be the derivative. You have to work it all out, right? Because you're so smart. You just do that little trick like where you drop it down, right? So what if I wrote this? The limit as h goes to 0 of sine of x plus h minus sine of x all over h. What's the function? Sine. What is the derivative? Cosine. And like we never even actually like did the algebra there, right? Because like we don't even know how. Like we have no idea. Like this is like a 35-minute problem to try to figure that out. It's super tough. So that's the function, and you come up with the derivative. You agree? Look at what you have. What's the function? You tell me when I get to the function. This is the function, right? What's the derivative? Look on the other side. You guys can get this. You can get this. Just stay focused here, okay? Notice the function was here. It was the thing being subtracted, right? The derivative is the thing that we said it's equal to that, right? So look. That's the function. What's the derivative? This. Look at this. This is incredible. What we've just said is that the derivative of this is the biggest part you need to focus on. The derivative of the area thing is the function right up above. That's incredible. A statement about f of x. Here's what we're going to state. Just we're going to do the area function. The derivative of the area function is the function that bounds the area. The derivative of the area function is the function up here that bounds it. So that means, if we want to make a statement about f of x, the antiderivative of f of x is the area function. Are you wondering what an antiderivative is? You already know what it is. F of x is 3x squared. Somebody tell me, what's the derivative? 6x. We all on the same page there? So now I'm going to ask you the antiderivative. We're going to write it as big F. What is it that you take the derivative of to get 3x squared? X cubed. That's the antiderivative. You see, if we could come up with the antiderivative of the function, we can evaluate the area lickety-split. That whole thing about adding up the area of an infinite number of rectangles, no need to even do it anymore. Let's see if you can figure out another one. I gave you 3x squared here. What if I have 5x to the 4th? What's the derivative? 20x to the cube. What's the antiderivative? Now you think you're getting pretty smart. How about I have this? How about x to the 6th? What's the derivative? 6x to the 5th. Take 30 seconds. See if you can come up with the antiderivative. Don't say it too loud. See if you can come up with the antiderivative. Just think about it. Go. 3, 2, 1. Folks, let's notice a pattern. What happens to the degree every time you take a derivative? What happens to the degree? You subtract 1, right? So if you're going to go this way, you're going to add 1. So we know it's going to be an x to the 7th, right? Anybody come up with it? X is 7th over 7. Yeah, or 1/7 x is 7, right? So what that means is this. If f of x is equal to x to the nth, then f of x, the antiderivative, we'll use big F to represent the antiderivative, is simply this. You take the exponent and you add 1 to it, and instead of multiplying, you divide by the new exponent. That's our rule for an antiderivative. Antiderivative does not mean you're afraid of a derivative. It doesn't mean you're directly opposed to derivatives. So, find the antiderivative of the following. F of x is x cubed. So what is big F of x? X to the 4th over 4. Look at you. F of x is 5x to the 4th. So big F is 5x to the 5 over 5, right? And so you get, as you said, x to the 5th. I add 1, I divide by the new exponent, so I'd have 4x to the 7th over 7. Oh, it doesn't work here, does it? How do you think we should write this first before we do that? 3 over 2 x to the negative 3. So the antiderivative is going to be, I add 1, so negative 2, right? And I divide by the new exponent. So you divide by negative 2. Dividing by negative 2 is the same as multiplying by? Yep, negative 1/2. So you can see that you get negative 3 in the top, and you get 4x squared in the bottom. Finding antiderivatives, no big deal, is it? Now, there's two parts of the fundamental theorem of calculus, and every professor I've ever known, they always teach part 2 on day 1. So that's what we're going to do. We're going to teach part 2. Forget about part 1. It's not as well known. Part 2 is what's really cool. And it says this. The integral from a to b of f of x dx. And we just spent a little bit of time figuring out how we evaluate that. Yeah, we added up the area of an infinite number of rectangles. It was super complicated, but you got really good at it because you're extremely intelligent. What do? Simple. We find an antiderivative, and we plug in b. And then we subtract that antiderivative evaluated at a. And that gives us the exact area. That's all we have to do. So we say where f is an antiderivative of f. That's the fundamental theorem of calculus part 2. So we're going to start with the most basic example. This was the first example we started with when we add up the area of an infinite number of rectangles. We did the area from 0 to 2 of x squared dx. In order to evaluate this, here's all you have to do. What's an antiderivative of x squared? X cubed over 3. And here's how we show that we're evaluating it at 0 and 2. We draw a line on the side. We put a 2 at the top and a 0 at the bottom. So this means we're going to take the antiderivative, we're going to evaluate 2, and then we're going to evaluate it at 0. We subtract in between. Plug in 2, and you get 8, right? 8 over 3 minus 0 over 3, which is 8/3. Wow. That's it. I ain't making it up. Look at this one. Do you know what 3x squared looks like? Does everybody know it's a parabola? Okay, we're going to bound it from 2 to 4. So like from 2 to 4, like that. Like you think about it, finding that area looks like it'd be something fairly complicated, right? And what we're going to do, I mean, you remember when you didn't start at 0, that was kind of tough, wasn't it? Well, now it's not going to be tough for us. We just find an antiderivative. What's an antiderivative of 3x squared? X cubed. Evaluate 4 and a 2. Plug in 4 and you get. Plug in 2 and you get 8. What's 64 minus 8? There's no way it could be that easy, right? Like, there must be a catch there. Like, if we actually try that on our calculator, if we go y equals and we go 3x squared, and we go calculate, and we go from 4 to 2, so we're going to do number 7. That's a shape. That's what I drew. I go 2, and I go 4. Tell me we're going to get something different than 50. No, we get 56. That easy. Oh, what about letter C? Yes, question. So I take the antiderivative of that. The way I take the antiderivative is I add 1 to the exponent, and I divide by the new exponent. We good? So the key is to start by finding an antiderivative. So in this situation, 3 roots of x. 3 roots of x. I need to write it so that there's an exponent. 3x to the 1/2. So if you want to find an antiderivative, be 3x to the 3/2 divided by 3/2. Now, dividing by 3/2 is the same as multiplying by 2/3. And when you multiply by 2/3, what happens? The 3's cancel, and you get 2x to the 3/2. So let's evaluate this. Let's see what we come up with. I plug in 2. 2 to the 3/2. What is 2 cubed? 8. The 2 underneath means square root. What's the square root of 8? 2 roots of 2 times 2. 4 roots of 2. Minus. Now let's plug in 1. What is 1 to the 3/2? Times 2? 2. That's the exact value. No estimation. Exact value. Oh no, we got all sorts of crazy stuff going on. We got x cubed minus x squared plus 2x minus 3. Yeah. Yeah. What, plug in 2? What's 2 cubed? 8. What's square root of 8? 2 roots of 2 times 2? 4 roots of 2. Good? Here I have more than one part. No problem. Just do each part. What's the antiderivative of x cubed? X to the 4th over 4. Minus, what's the antiderivative of x squared? What's the antiderivative of 2x? What's the antiderivative of 3? 3x. So if you write it as 3x to the 0, that's what 3 is, right? If you add 1 to the x, or to the exponent, you get 3x to the 1, and you divide it by 1. I like to just think about it, what would you take the derivative of in order to get 3? And you take the derivative of 3x. Evaluate it at 1 and 0. What do you get if you plug in 1? 1/4 minus 1/3 plus 1. Common denominators, 12. So 3/12 minus 4/12. And then 1 minus 3 is -2. So minus 24/12. Three minus 4 is -1. Minus 24 is -25/12. What does that mean? What, we came up with an answer here we've never come up with before. Negative. What do you think that means? Can you have negative area? In calculus, you can. What it means is that the area sits below the x-axis and not above the x-axis. And we'll talk more about that later. What's the antiderivative of sine? Is it cosine? Which one is it? Cosine or negative cosine? It's negative cosine. What's the derivative of cosine? Negative sine. So I'll write out the chart for you, okay? So you may want to consider doing this. If you're ever wondering about sine and cosine, here's what a lot of people do that kind of helps them out. They write sine of x, cosine of x, negative sine of x, and negative cosine of x. What's the derivative of sine? Cosine. Because you could go this way, right? Like, that's no problem. Derivative of cosine is negative sine. Derivative of negative sine, negative cosine, and then the derivative of negative cosine is sine. So this tells us everything we need to know in order to go this way. This says right here that the antiderivative of cosine is sine. See that? So the antiderivative of cosine is sine. Yeah? Yep, I just wrote sine. If I take the derivative of sine to get cosine, then that means the antiderivative of cosine is sine. So the antiderivative of cosine is sine. The antiderivative of sine is the antiderivative of negative sine is cosine. The antiderivative of negative cosine is. So if that helps you, you can kind of keep track of that. So let's try that. The antiderivative of sine is cosine. We got to plug in pi. What's the cosine of pi? What is it? 1 or negative 1 or 0 or what? It's negative 1. So we got negative negative 1 because of the negative sign. Minus. Then we plug in 0. What's the cosine of 0? 1. And the negative makes it negative 1. So we have positive 1 plus 1 is 2. Two more. I got 2x to the negative 2. What's the antiderivative? Two x to the negative 1 over the antiderivative of 2x to the negative 2 is 2x to the negative 1 over negative 1. Yes? So I would have negative 2 over x. We're going to evaluate it at 5 and 1. I plug in the 5, I get negative 2/5 minus, and then you plug in 1 and you get negative 2. People see that you can make mistakes with your positives and negatives in this scenario. Got to be careful. So we have negative 2/5 plus 2, or negative 2/5 plus 10/5, which is 8/5. Where is this function undefined? At 0. Is 0 included in the interval of 1 to 5? No. Where is this function undefined? Is that included in the interval of negative 1 to 6? So therefore, you cannot do the fundamental theorem of calculus. The FTC does not apply. In order for the fundamental theorem of calculus to work, you have to have a function that's continuous over the entire interval. If it is not, then the method does not work. It doesn't mean we can't find the area, but we can't do it using that same piece. Good job. Take out your worksheet.